Gemini 3 was the spacecraft for America's first two-man flight in space.
Right, computer. Set up on 324. Ready for program sequence?
Okay, understand you are complete.
That's affirmative.
The final countdown was heard and witnessed by millions throughout the world. It was the culmination, the final effort to assure safety for the crew and success for the mission. It followed years of design, manufacture, and pre-flight preparations, including simulated countdowns, witnessed only by the test engineers and technicians of NASA and private contractors, the men and women who share the ultimate responsibility for crew safety and mission success. They performed the thousands of precise tests necessary to assure a safe, reliable spacecraft. This film documents some of these vital tests using Gemini spacecraft in scenes of pre-flight preparation, testing, and checkout to guarantee that before men are rocketed into space, all systems are go.
Electrical lead.
Go.
RF lead.
Go.
Instrumentation lead.
Go.
Playback.
Go.
Before Gemini's two-man missions were possible, the United States had to master the technology required to place one man in Earth orbit. This was done in the Mercury program, which gave us the experience, the overall success, and even the occasional failures which paradoxically help establish the most effective pre-flight test procedures. For example, the unmanned Mercury Atlas III. Despite booster failure, the escape tower lifted the spacecraft from the exploding launch vehicle, offering dramatic proof of the success of thorough testing of astronaut safety devices built into manned spacecraft systems. The 6 manned flights of the Mercury program accomplished their missions and achieved a 100% record for astronaut safety. Before such a record can be made, before manned space missions can be launched and completed successfully, the most painstaking preparations must be made, unlike those for any other flight vehicle, from aircraft to intercontinental missiles. Each man-rated spacecraft requires a uniquely diverse, complex, and exacting test program to assure both mission success and crew safety. There must be an organization of specialists in every field of space technology: engineers, inspectors, technicians, managers, and support personnel, combining their skills in each tremendous effort to make sure that the next logical step toward America's goal of preeminence in space will be achieved. The next step for the government industry team that proved out Mercury involved the even greater challenges of Gemini. The Gemini spacecraft is of a modular design that lends itself to the building block philosophy of testing. There are 2 major modules, the reentry module and the adapter module. The reentry module is composed of 3 sections: the rendezvous and recovery section, the reentry control section, and the cabin section. The adapter module contains 2 sections, the retrograde section and the adapter equipment section. Months before any of the 5 sections of the spacecraft can be assembled, the Gemini test program begins. Thousands of firms throughout the United States perform pre-delivery acceptance tests on parts and materials. Pre-installation acceptance tests are performed after delivery to the prime contractor. These constitute an enormous test effort in themselves. The focal point for these thousands of Gemini suppliers and subcontractors is the St. Louis plant of the spacecraft's prime contractor, the McDonnell Aircraft Corporation. After pre-delivery and pre-installation acceptance testing, there are several phases of the Gemini spacecraft test program, at the McDonnell plant and at the launch site. At McDonnell, there are tests of components, subsystems, and systems in sections before they are mated together to form modules, then tests of modules before they are mated to form the complete spacecraft. These are followed by combined and integrated tests after modules of the spacecraft have been assembled and mated together. At NASA's Merritt Island Industrial Area in Florida and at the launch pad, preparation and tests of the assembled spacecraft and the mated spacecraft and launch vehicle culminate in the final countdown and launch. The following scenes at the McDonnell plant in general document the test history of the Gemini 3 spacecraft. Procedures on other spacecraft vary in the depth of testing. For example, since number 3 was the spacecraft for the first two-man mission, many subsystems tests were performed before assembly of sections into modules, then confirmed in testing of the modules. Such tests in subsequent spacecraft are performed only after the subsystems are installed in the modules. But each test program follows the building block pattern as units progress from modular tests through combined and integrated tests of the complete spacecraft. As we have noted, the subsystems of each section are carefully checked out before they are installed in the sections. The series of tests then performed on each of the 5 sections of Gemini 3 are outlined as follows. Beginning with the rendezvous and recovery section, after assembly, it is first subjected to a voltage standing wave ratio test, verifying the effectiveness of its radio frequency paths. Tests are then conducted to check out the section's electrical system. A test console verifies proper operation of electrical circuits, including parachute separation switches. The section is then weighed and balanced to determine its total flight weight and center of gravity. After its assembly, the re-entry control section undergoes tests to validate the section's radio frequency paths and instrumentation, including sensors, thermocouples, and switches. Then, to verify correct installation and integrated operation, complete validation and functional tests are conducted on the re-entry control system. All lines, valves, and components are subjected to the pressures and flow rates they will experience during re-entry. After the cabin section is assembled, 9 major test series are performed on it. Cabin coolant systems undergo leak and validation tests. The primary and secondary coolant systems are pressurized with nitrogen and helium, and any leaks or decays in pressure are detected. Then a voltage standing wave ratio test verifies the operational capability of all radio frequency paths, and a complete electrical system test verifies all components of the cabin section's electrical power system. This test also checks electrical connections with a simulator for the adapter module. Next, telemetry transmitter tests are monitored by consoles in the control room to ensure that both real-time and delayed-time transmitters are operational. A cabin instrumentation test provides initial testing of all instrumentation equipment in the cabin, from pressure and temperature indicators to biomedical instruments. After the instrumentation test, the cabin section is subjected to a sequential system test. This test uses light indicators and recorders and simulators for other spacecraft sections and the launch vehicle. By simulating events of both normal and aborted missions in sequence, the test verifies that cabin systems will respond to all stimuli from launch to impact. The cabin section communication system is then completely checked out. Final cabin section validation and functional tests are conducted of the environmental control system. The 3 sections of the re-entry module are then mated. The module is weighed and balanced. Later, optical alignments are made. For example, the horizon sensors are aligned with the inertial guidance platform. Optical sightings are made to obtain the exact alignment. In the meantime, before the re-entry module can be mated with it, the adapter module must be thoroughly checked out. Its electronic systems are verified in telemetry transmitter tests. Instrumentation tests are performed, as are coolant system validation tests. Tests of communication systems determine their functional capability, and an adapter section sequential system test, using a simulator for cabin section functions, verifies the response of adapter systems to all launch and flight stimuli. The fuel cells carried in the adapter to provide electrical power on long-duration missions are given several tests, including vibration, such as the test going on here. Also located in the adapter is the orbital attitude maneuvering system, shown during an initial qualification test on an air-bearing table. Adapter guidance and control system tests for all mission modes verify the wiring to the orbital attitude maneuvering system, and validation and functional tests verify all operational requirements of the so-called OHMS system. The primary oxygen system in the adapter equipment section is checked out. A functional test is made of the adapter coolant system and temperature control valves. Weight and balance measurements and retrograde rocket alignments follow. When the functional integrity of all spacecraft sections has been proved out, a formal spacecraft acceptance review is held by NASA and contractor engineers. Spacecraft status is evaluated and discrepancies are noted. After all necessary rework and verification tests are completed, the adapter and re-entry modules are mated. Tests at the contractor's plant following mating of the spacecraft include validation of the complete integrated spacecraft coolant system, radio frequency tests to verify the operational capability of radio systems in the mated sections and modules, environmental control system servicing for the complete spacecraft, and systems assurance tests to verify correct mating and the accuracy of tests that use simulators to take the place of spacecraft sections or modules. Tests of the guidance and control system are then conducted, in which all operational modes of guidance and control are verified, and all interfaces of the system with other spacecraft sections are checked out. Participation of astronauts in guidance and control checkouts is just one example of another key point in test philosophy, which considers the flight crew an integral part of flight systems. Further leak and validation tests are conducted on the integrated re-entry control system and orbital attitude maneuvering system. To correct discrepancies or malfunctions revealed in tests up to this point, all necessary factory rework is performed. This manufacturing rework activity is followed by the most comprehensive factory test, a simulated flight test exercising all systems in sequence through all phases of an aborted mission, then through all phases of a normal mission from launch to impact. In this realistic simulation, the spacecraft must be proved operationally ready for its mission. The final test at McDonnell is a manned altitude test. The main purpose of altitude chamber tests is to determine how well components of the environmental control system will function when pressures are equal to those of actual flight. In a separate control room, consoles monitor and record data, including crew medical data. Of course, the immense multiplicity of details making up factory testing are too numerous to present in one brief film review, and it is difficult to convey the care and complexity of test operations as performed by contractor personnel and monitored by NASA system engineers at the McDonnell plant, and additional specialists called in from time to time. Planning and scheduling meetings must be held daily to maintain management control of testing and to ensure efficiency. Facilities and test equipment must be available on schedule. Aerospace ground equipment must be constantly tested, qualified, and calibrated. There must be test procedures, progress reports, inspection and test records, and documentation of work orders, discrepancies, and malfunctions. There must be detailed records of component specifications, performance data, and shelf life. Qualified spare parts must be on hand to avoid lost time. Test data must be monitored, recorded, and evaluated. Engineering design changes must be coordinated between systems test engineers and design engineers. Attention to vast amounts of detail and close-knit teamwork are required to make a spacecraft flight-worthy. To recapitulate pre-flight acceptance testing at the factory, let us briefly go back and follow the course of just one GEMINI subsystem, the environmental control system. The manuals containing factory test procedures and revisions on the environmental control system comprise several hundred pages. Before the system is installed in the cabin section of the re-entry module, a pre-installation acceptance test of the complete package is conducted. Validation and functional tests of the installed system are then undertaken to verify systems operation. The system is checked for leakage, and pressure readouts are calibrated. The procedure is as follows. First, there is a water system leak check. Suit circuits are checked for leakage, then given functional tests. Suit circuit low pressure and medium pressure oxygen systems, including primary oxygen supply lines, are leak tested. Checks are made for secondary oxygen leakage and functional operation. Pressure is evacuated, decay rate monitored, and transducer calibration is verified. Finally, a cabin leak check is conducted. The cabin is again pressurized, leak rate is monitored, and transducer calibration verified. Various tests are also performed on the environmental control system's primary oxygen supply, which is carried in the adapter equipment section of the adapter module. In functional and leak tests, the adapter oxygen system is pressurized. Leak checks are conducted on lines and connections. The system is again pressurized and leak tested at operating pressure. Transducer calibration is then verified by depressurizing in measured increments. In the primary oxygen functional test, the output from the primary oxygen regulator is checked to verify that output flow and pressures will meet maximum flight requirements. One more series of tests is conducted before mating the spacecraft, a complete checkout of the coolant loop system located in the adapter. After the mating of the adapter and re-entry modules, further tests of the environmental control system include the following. The mated coolant system is serviced. In the process, the spacecraft system and connected servicing equipment are evacuated. The system is filled with coolant, and a sample is drawn and analyzed to verify acceptable cleanliness. A functional test is made of coolant flow rate and temperature control valve operation by imposing known heat loads on the spacecraft system from connected servicing equipment. Several more factory tests are required to complete environmental control system testing. One of these, as we have seen, is the final altitude chamber test, which verifies the correct operation of those environmental control system components which require an evacuated environment for operation. Following altitude chamber tests of the assembled spacecraft, a final factory review is held. Each of the 5 sections is carefully inspected, and the spacecraft is prepared for shipment. It is then taken to the transport aircraft, loaded in the aircraft, and sent on its way to Cape Kennedy. With delivery of the spacecraft to the Kennedy Space Center, a change in test philosophy from that of the Mercury program was initiated with GEMINI. It is no longer considered necessary to repeat certain tests in the industrial area which have already been successfully performed at the factory. However, Gemini 3, as the first manned Gemini spacecraft, was subjected to some tests not programmed for subsequent spacecraft. In the Florida test program, a complete integrated checkout of the spacecraft is conducted. Receiving inspection operations at the Merritt Island industrial area reveal any damage from shipment and handling. The spacecraft's records are verified, that is, checked against its particular specifications. Installation is verified of nozzle plugs, vent caps, and other units, and any other special inspections are performed. Following receiving inspection, the rendezvous and recovery section of the Gemini 3 spacecraft was temporarily mated to check out antennas, switches, and cables. From the receiving checkout area, the Gemini 3 spacecraft was moved to the RF Systems Test Facility for special communication radiation tests. With the flight crew again serving as part of the control loop, access doors were secured, and the spacecraft in flight configuration was subjected to a high-frequency radio test to verify proper operation of all electronic systems. Various other radio frequency tests were then conducted. The wooden tower was cleared of all non-essential metallic objects such as cables to ground power supply equipment. Spacecraft systems were operated on internal power. The tests ensured that radio transmission and reception were free from interference from any source in the spacecraft. For this purpose, electronic, electrical, and mechanical components and systems were activated during the tests. Following radio frequency range tests, the Gemini 3 spacecraft was moved to the fluid test complex. Aerospace ground equipment was connected, and various tests were conducted to assure spacecraft propulsion systems operation. The orbital attitude maneuvering system and the reentry control system were serviced with propellants. Thrusters of these systems were static fired. The systems were then deserviced and inspected. The spacecraft was next moved to a pyrotechnic installation building for installation of explosive devices. The rendezvous and recovery section, with parachutes installed, was permanently mated to the other 4 sections of the spacecraft. Explosive actuators and igniters were installed. A spacecraft cleanup was performed, and a gross weight and balance check was conducted. A complete overall inspection marked the conclusion of industrial area tests. In the meantime, the launch vehicle, a modified Air Force Titan II, has been flown from the Martin Company in Baltimore, Maryland, to the Cape, unloaded, moved to Complex 19, and erected on the pad. Extensive tests and checkouts, of course, are also given the launch vehicle. Before a spacecraft is erected at the pad, the launch complex is given a complete checkout, along with aerospace ground equipment required for pad tests. For this last phase of pre-flight testing, the spacecraft was moved to Launch Complex 19. On arrival at the pad, the spacecraft was hoisted to the White Room at the top of the erector. In the White Room, temperature and humidity are carefully controlled. Maintaining cleanliness also is of critical importance. Work platforms were emplaced. The spacecraft was positioned on the erector tripod about 6 feet above the launch vehicle so that initial tests could be conducted before mating the spacecraft to the vehicle. Aerospace ground equipment cables were connected. The spacecraft was loaded with its cryogenic oxygen, and a pre-mate systems test was conducted to prove all systems flight-worthy and to verify compatibility of spacecraft and launch pad aerospace ground equipment. Next, a pre-mate simulated flight test was conducted, proving that spacecraft systems would operate in sequence through selected phases of a mission. Pre-mate interface inspections were conducted, followed by preparations for mating. Then the spacecraft was mechanically mated to the launch vehicle. In the course of electrical mating, interface and validation tests were conducted. A joint combined systems test proved compatibility of the spacecraft, launch vehicle, and launch complex, and tests verified umbilical ejectability and other programmed performances. Extensive preparations were then made for a complete simulated launch test of the combined spacecraft and launch vehicle. Both cabin and adapter oxygen supplies were serviced and tested. Suit tests were conducted. Radio frequency compatibility tests were conducted. The reentry control system and the orbital attitude maneuvering system were serviced with their flight loads of hypergolic fuel. The simulated launch test, called a wet mock, was a complete 4-day checkout of the entire space vehicle and launch procedures. Following the wet mock simulated launch and final systems tests, separate flight readiness review meetings were held for both spacecraft and launch vehicle. A final simulated flight test was then conducted. Except for simulation cables and disconnected explosive devices, the spacecraft was in actual flight condition. In this simulation, the combined Gemini 3 space vehicle, the launch complex, the worldwide tracking network, and mission control participated. The integrated operations of all systems, including the onboard crew, were verified in various flight modes. After final simulated flight test, an overall review by the Mission Review Board, composed of key personnel of NASA, the Department of Defense, and contractors, certified the space vehicle ready for launch. Following commitment to launch, final preparations were made for the countdown. With power up, the final countdown proceeds. The final, orderly, careful procedure of pre-flight testing.
Mod 3.
3, go.
Mission monitor.
Go.
Project engineering.
Go.
Pad safety.
Bad safety, go.
SRO.
SROs, go.
Roger. Spacecraft test conductor.
Roger, all systems are green and go.
At T-minus 3 minutes, the onboard computer receives the latest updated launch data. At T-minus 10 seconds,
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
A flight-worthy spacecraft, a reliable launch vehicle, a coordinated mission success. As the United States moves forward in the mastery of spaceflight technology, forward to the completion of extended GEMINI missions, Apollo orbital and lunar landing missions, and advanced programs for the manned exploration and peaceful use of outer space, the government industry specialists of spacecraft pre-flight testing will continue to assure safety for our crews and success for our missions.